Identification of stereoisomers and relationship between two given molecules. By the end of this video, you should be able to give the relationship between two given molecules and to identify stereoisomers. And even if they are constitutional isomers, you should be able to tell. Let's start with chirality. A chiral carbon is a carbon with 4 different groups attached to it. So to identify a chiral carbon, you will be looking at a carbon that has 4 different substituents and has no line of symmetry. So let's look at this molecule. This carbon has 4 different substituents. There is a hidden hydrogen here. If you look at this carbon, it's a metal group. There are 4 hydrogens, 3 hydrogens attached to it. Hydrogens repeating makes it non-chiral. This carbon has 2 hydrogens. This carbon, same to this, same to that, and same to this and this and that. And this has 3 hydrogens, so it cannot be chiral. So this carbon is joined to a bromine and a hydrogen, which are different. And 1, 2, 3, 4. 4 carbons. 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons, which means there is a line of symmetry. If we divide this one right here, we are going to get 4 carbons, half of hydrogen, half of bromine, 4 carbons, half of hydrogen, half of bromine. So this carbon here is achiral. What about this? Looking at this, carbon here with hydrogen and with an ethyl group and a methyl group and a long chain. This carbon is chiral. What about this? Hydrogen, a long chain which is longer than this, and this chain has substituent. This chain has no substituent. So this carbon is chiral. Because this molecule has, no chiral center, it has no chiral carbon, then the molecule is achiral, right? It's an achiral molecule. This molecule has chiral centers, so the molecule, and there is no line of symmetry, so the molecule is chiral molecule. What about this? We are looking at carbon with 4 different substituents. This carbon here has bromine, hydrogen, and a methyl group with a long chain. This carbon atom here is chiral. So it's chiral, making the molecule a chiral molecule. Well, you can determine the number of potential stereoisomers with a given number of chiral centers. Is 2 to the power n, where n is the number of chiral centers in the molecule. This molecule has no chiral center. This molecule has 2 chiral centers. So the total stereoisomers that we can get in this molecule, in this molecule here, is 2 to the power 2, which equals 4 stereoisomers. It could be Rs, it could be Sr or Rs or Rr or SS. So 4 possible stereoisomers. That is another thing you should know. For this molecule here, it has 1 chiral center. To determine the number of possible stereoisomers is 2 to the power n, where n equals the total number of chiral centers in the molecule. So here we have 1, so it's going to be 1. It's going to give us 2. So it's either going to be an S or R. If it is 1 chiral center, you'll be comparing it to S or R. If it's 2 chiral centers, you'll be comparing it to RS and be changing it, right? RS, SR, SS, RR. If it is 3 chiral centers, you start comparing by R, 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 then R, RS, then R, S, S, then R, S, R, up to a point. If this is where you will get the total number of stereoisomers. Remember, we are talking about 3 So 2 to the power 3 gives us 2 by 2 by 2. So we should have 8 stereoisomers in total, possibly. Let's generate this and see. We are looking at 8 stereoisomers. 3 means 3 chiral centers, so we have to start by 3 of those. R, 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 S. So R, S, R. So S, R, R. Now let's start with S, 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 S. So S, S, R. So S, R, S. So S, S, that it should be R, S, S. So in total, with 3 chiral centers, we can get 1, 2, 3, 4, 5, 6, 7, 8 possible stereoisomers. So if our chiral centers would be 4, 2 to the power 4 gives us what? 2 by 2, 4, 4 by 2, 8, 8 by 2, is that not 16? So we should start, since the chiral centers are 4, we should start with 4 of those, 2, 3, 4, and start varying. So what is the relationship between these two molecules? Are they enantiomers, diisomers, distereomers, or Meso compound? Now, here the molecule, this side of the molecule is on the dash wedge, and the same side of the molecule, the configuration turned totally to solid wedge. So these two molecules are enantiomers. Let's say here, if the configuration of the molecule is R, which is on the dash wedges, it will change completely to S. Then it means the two molecules are enantiomers. So you can just look at the molecules. Let's look at their spatial arrangement. Here it's on the solid wedge, dash wedge, and here the same is on the solid wedge. But don't forget the substituent that on it. They have the same fluorine. So that's where solid wedge, there are enantiomers because their configuration has changed. Another way to look at this is to indicate the R and S configuration of the chiral carbon. Looking at this, the chiral carbon has 4 groups attached to it. 4 groups attached to it. We indicate priority. Priority of the substituent are indicated by atomic number. The one with the highest atomic number will take number 1. Fluorine has higher atomic number as compared to methyl group and a propyl group. So fluorine number 1, and this will be number 2, and this will be number 3. There is a hidden hydrogen here. We don't know whether it's on the solid way, but that's right. There is a hidden hydrogen there. So now priority is from number 1 to 2 to 3. So now let's see, 1, 2, 3. You could see that it's going counterclockwise. So counterclockwise, when it's going counterclockwise, it is an S configuration. But when it's going clockwise, it is an R configuration. But after that, we have to look on our last priority group, the 4th priority group. If it is on the dash wedges, we have no problem. If it is not on the dash wedges, if it's not on the dash wedge, we have to reverse the configuration. So we said this is an S configuration, but it's our least priority group on the dash wedge. No, it is on the solid wedge. So we have to reverse the configuration to R. So this chiral carbon is an R chiral carbon. So now let's look at this. Assuming we have hydrogen here. So let's indicate priorities. 1, and this will have priority number 2, and this will have priority number, methyl group will have priority number 3, and the hydrogen will have the least one. The hydrogen is not indicated here, it means hydrogen is at the back here. Yeah, so you can decide to bring it here, no problem. Anyway, this is our priority number 4. So let's start counting from 1 to 2 to 3 in order. 1, 2, 3. So you can see that it is going counterclockwise. So this is an S. If it's going counterclockwise, it's an S. If it's going clockwise, then it's an R. So this is an R configuration. But let's look at our least priority group. Is it on the dash wedge? Yes, hydrogen is on the dash wedge, so there's no need to change the configuration. So in an exam problem, all the centers will be indicated very well for you to analyze it very well. So it won't be given to you like the hydrogen that wasn't here and I indicated it. Everything will be given to you intact for you to be able to analyze it. So since here the molecule is an R and here it's an S, the configuration has changed totally. Then the two molecules are enantiomers. That is another way of looking at it. But you can just look at the molecule. Since fluorine here is on a dash wedge and here it is on the solid wedge, they are enantiomers. So if the molecule has chiral center, it's either, they can be an enantiomer or enantiomers, diastereomers, or Meso compounds. Let's look at this. So what the relationship between these two molecules, the relationship between these two molecules. So you will see that they all have, chlorine here, but what is happening? Here they were all on the dash wedge, but here they are on the solid wedge. What is happening? You will see that this carbon atom here is chiral, this is chiral, this is chiral, this is chiral. But don't forget line of symmetry. The molecule may have chiral centers chiral centers and still not be chiral, depending on the symmetry. So you see that you can totally divide this molecule into two, and you get what is at the left hand side will still be the same as what is at the right hand side. Solid weight, no problem. Solid weight, no problem. Here, that's wedges. You can divide it into two, and you get what is here to be what is there. So these two molecules are Meso compounds. What about these molecules? Let's say bromine. Now, looking at these molecules, do they have a line of symmetry? No, because if you divide this molecule into two, you get the bromine here to be on the dash wedges, by bromine here will be in the solid wedge. So here dash wedge, here solid wedge. You can divide them into two. But what is happening? You will see that one of the um, center has changed. Here bromine is on the solid wedge. If you compare it to this molecule, bromine should be here on the solid wedge. This side of bromine here is on a dash wedge, but here this side of bromine is on the solid wedge. So you can see that the chiral centers have changed their configuration, right? So these two molecules are enantiomers. What's the relationship between these molecules? So here in this molecule, the chlorine atom is on the solid wedge, and here it is on the dash wedge. The configuration has changed totally. So these two molecules are enantiomers. Total change in configuration. They are enantiomers. What about this? All the bromines here are on the dash wedge. By here, one of the bromine changed into a solid wedge. If at least one of the configuration change, but not all, then they are stereoisomers. Stereoisomers. They are distereoisomers. As one of the configuration change, but not all. If all the configuration change, then they are enantiomers. But if at least one of the configuration change, not all, then they are diastereomers. What about this and that? Now we have the alcohol group on this carbon here. The OH group on this carbon here, on the second carbon from the right, and the OH group is on the third carbon on this molecule. What are you seeing? The functional group has rearranged itself. For constitutional isomers, they have different connectivity. But for stereoisomers, they have the same connectivity of atoms, but different arrangement in space. And this is what will be defining the arrangement in space. But these ones, they are constitutional isomers because constitutional isomers. So don't forget, because they have different connectivity. The OH group here is on the second carbon, but here it is on the third carbon. What is the relationship between these molecules? This is a bromine, this is the bromine. Here, you could see that all the bromine atoms are on the solid wedge, but here they are on the dash wedges. The configuration has changed totally, and when this happens, they are enantiomers. Enantiomers. And here, one of the OH group here is on the dash wedge, and the one here is on the solid wedge. If you compare it to this side, the OH group here, which is on the dash wedge, is now on the solid wedge here. And this one, which is on the solid wedge, is now on the on the dash wedge here. So what is happening? The configuration has changed totally, because this one right here is on a solid wedge here, but here it's on a dash wedge. And this one here is on a dash wedge, but here it's on the solid wedge. So try to figure that out. The configuration has changed totally. So there are enantiomers. I know you are wondering about this. Sometimes that's how it is. If you don't take care, you are going to confuse yourself. After that, you have to be looking about, of line of symmetry in this problem here. You know, they are all on the solid wedges, but there is a line of symmetry. There is a line of symmetry. That is one thing you don't have to forget. I intentionally leave it to see how you'll be thinking. Don't forget line of symmetry. If there is a line of symmetry that can divide them, what is on the solid wedge here is also on the solid wedge here. What is on the dash wedge here is also on the dash wedge here. Then they cease to be enantiomers. They become Meso compounds. So they become Meso compounds. But here, is there a line of symmetry? No. Because if you divide this molecule into two, the one here will be on the dash wedge, the one here will be on solid wedge. So they cease to be equal. The same thing happened to here. But you could see that the configuration here has changed totally when it comes here. This here is on the solid wedge, this here is on dash wedge, it has changed. This here is on the dash wedge, this here on the solid wedge, which means it has changed. So there are enantiomers. What about this? Now bromine here is on the solid wedge, bromine here is on the solid wedge, bromine here is on the dash wedge, bromine here is on the solid wedge. So one of the configuration has changed. Bromine solid here, no problem. Bromine dash here, bromine solid here. It means one of the configuration has changed, but not all of them. If it should be all of them, this on the solid here should be on the dash here, and this on the dash here should be on the solid here. But no, that didn't happen. This on the solid here is still on the solid here, and this on the dash here decided to change to solid. So at least one of the configuration has changed, but not all. So they become diastereomers. Diastereomers. Stereoisomers. Diastereoisomers. What about these molecules? Can you tell the relationship between? Now let's look at the arrangement of the atoms. Chlorine is on this carbon here. Chlorine is on this, the interval. There's no atom between them, right? But here you could see that there is one carbon atom between chlorine here and chlorine here. So they have different arrangements, right? So they are constitutional isomers. Constitutional isomers. You have to observe the molecules very well. Problems like this are easier, but you have to observe the molecules very well. Look at the spatial arrangement. Don't forget to look for a line of symmetry or planar symmetry that divide the molecule into two. A plane of symmetry. Now, what is the relationship between these two molecules? Well, we have hydrogen on the dashes here, but the configuration changes totally here to solid wedges. Now we can say these molecules, since the configuration here has changed totally here, then they are enantiomers, right? That is what we can see. But don't forget a line of symmetry or any symmetry that will divide the molecule into two equal parts. So looking at this, is there a line of symmetry? Yes, because we can divide this molecule into two equal halves. And the same can happen to this. So once there is a line of symmetry, these two molecules are Meso compounds. So if the two compounds that you are comparing them, if they have chiral carbons, if they are not enantiomers, they will be either Meso compounds or they are identical. So before we end this video, let me enlighten you on this. If let's say the configuration here is RS, one of the molecules is RS, and the configuration of the other one is SR, which means it has changed completely, right? So RS is not the same as SR. So they are enantiomers, right? Enantiomers. Here we could have said they are enantiomers because here they are on the dash wedges and here they are on the solid wedges, which means the configuration has changed completely. Dash wedges, here solid wedges. We could have said they are enantiomers because the configuration has changed completely. But because there is a line of symmetry, they cease to be so. They cease to be so. What if we have RS and here we have this one to be RS and here to be SS? It means only one of the configuration has changed. Here the R here has changed to S here. So they become diastereomers. Diastereoisomers. Isomers. If the configuration of this is RS and the other one to be RS, then the molecules are identical. Finding problem with R and S configuration, check my video on that. I have a video on that, and facial projection problems too, which might help you. I have a lot of videos under stereochemistry, including the frontier molecular orbital theorem using it to predict reaction, pericyclic reactions, zygmatropic rearrangement, chirality centers, polarimetry calculations. So feel free to check on those videos if there is a need to. So that is it for this video. See you in my next video. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.